Some properties of atoms are easiest to observe in a gas. But at room temperature, the atoms in a gas are moving at around 1 kilometer per second, a speed that makes them difficult to study. Physicists would like to slow them by lowering their temperature. Conventional refrigeration techniques can get atoms down to a few thousandths of a degree above absolute zero. But what if you could cool the atoms even further? The 1997 Nobel Prize in Physics was awarded for doing just that to Claude Cohen-Tanuji, William D. Phillips, and Stephen Chu. The techniques they developed in laser cooling and trapping have allowed physicists around the world to explore matter at temperatures measured in billionths of a degree above absolute zero. In Cambridge, Massachusetts, at MIT, physicist Martin Zweierlein and his team are using these techniques to explore some of the fundamental properties of matter.
These ultra-cold atom experiments are very versatile, and they can be run by just a couple of students. Here we can prepare a model system, atoms, in all kinds of different configurations, with all kinds of partners, with a mixture of different atoms, to understand really how matter behaves.
With this system, Zweierlein performs different tests on these atoms, tests that can probe characteristics of matter that have, until this point, been purely theoretical.
So it will be a back and forth between theory and experiments. The theorists come up with a model, the experimentalists realize that model, and we can match theory and experiment in a quantitative way.
Zweierlein's research focuses on a broad classification of particles called fermions.
All massive elementary particles are fermions. They build everything we see around us. Ourselves, the sun, neutron stars, the universe. So that's why they are the fundamental particles to study.
Specifically, Zweierlein is interested in fermions that are strongly interacting, which means that they are strongly attracted to one another.
Fermions with strong interactions turn up in all kinds of systems in nature. We find it in the beginning of the universe, in a split second after the Big Bang, and the atomic nucleus itself is a strongly interacting Fermi system where protons and neutrons pair up, or inside a neutron star. We cannot fly to a neutron star, we cannot zoom into the atomic nucleus unless we build a huge, very expensive collider. But we hope to have a model system using our atoms as model matter in the lab to probe these strongly interacting fermions in a well-controlled environment.
Strongly interacting fermions are being studied in the laboratory by cooling and trapping cold clouds of atoms. Theorists predicted that dilute fermionic gases form what is known as a superfluid at very low temperatures. Superfluids are a peculiar and counterintuitive state of matter which flow without resistance or friction. First discovered in 1938, superfluid helium has been studied extensively. Here you can see that the liquid helium flows upwards, out of the bottle. Even though liquid helium can form a superfluid state, and past experiments have yielded indirect evidence of fermionic gases acting as superfluids, there had never been direct confirmation of this theory, until Zweierlein's group conducted an experiment with lithium atoms. The first step? Cooling them to temperatures less than 1/1,000,000th of a degree above absolute zero.
The whole experiment starts at very hot temperatures, actually, inside an oven that is here wrapped in aluminum foil because it's really hot. I don't want to touch this. That's where we have a block of metal that we heat up to 450 degrees Celsius. So you might think this doesn't really bring you very close to ultra low temperatures, but this is where we create a gas that we can then cool later in the machine.
After the metal is heated to a very hot 450 degrees Celsius, fast-moving atoms enter a 1-meter-long tube from which they exit at 1/1000th of a degree above absolute zero. To cool the atoms this dramatically, Zweierlein's team exploits the quantum mechanical property of atoms to absorb and give off energy only at certain frequencies. Within an atom, electrons occupy quantized energy levels. This means an electron can only have certain amounts of energy, dictated by the rules of quantum mechanics. Electrons can leap between these energy levels by absorbing or emitting photons. If the atom absorbs a photon with an energy equal to the difference between two energy levels, the electron can move from the lower level to the higher level. Likewise, an electron can jump down to a lower level by emitting a photon. In the process of absorbing a photon, the atom receives a small push, a push in the direction away from the source of light, which is the key to laser cooling.
Now comes the magic of laser cooling. We bombard these hot atoms with laser beams that are resonant with the atoms. The atoms absorb all this laser light, which we think of as photons, little particles, light particles that bombard the atoms. And every time the atoms absorb one of these photons, they get a recoil kick. So they slow down. And they do that 10,000 times from the oven to the chamber over here.
Zweierlein's apparatus, the laser beam shoots photons in the opposite direction of the atomic beam. When an atom absorbs the photon, momentum is transferred and it slows down. When an atom re-emits that photon, it is emitted in a random direction. As the atoms are continuously absorbing photons coming from one direction and re-emitting photons in random directions, the net result is a loss of momentum in that direction.
And over the length of 1 meter, we are able to slow the atoms from 450 degrees Celsius to 1 millikelvin. That's 1,000th of a degree above absolute zero. A millikelvin is cold, but surprisingly not cold enough for us. We need to cool to a few billionths of a degree above absolute zero. So this chamber of the apparatus is where all the action happens. This chamber is at ultra-high vacuum. We make sure that there are no other atoms than the ones we want to study in there. There are no air particles in there. Actually, the vacuum is so good that only 100,000 atoms per cubic centimeter are in there. Sounds still like a lot, but it's nothing compared to the 10 to the 23 whatever atoms that you have in a solid per cubic centimeter. So it's extremely empty inside.
The cooling inside the chamber takes place in several steps. First, the slowed atoms are captured in what is called a magneto-optical trap. They use 6 laser beams, all intersecting in the center of the chamber. No matter which way the atoms move, they will find a laser to guide them back into the trap. In the trap, the atoms lose more energy and reach lower temperatures. But the ultimate temperature they can reach in the laser trap is limited, and they will still need to be cooled further.
So it turns out, inside this chamber we then switch off the lights and trap the atoms in a magnetic trap, using coils like this one wrapped around the chamber to produce a magnetic field. And they're stored happily forever just because they have a little magnetic moment. So there is a nice analogy in classical mechanics, which is called the levitron. This is this little top here. It's a magnet that floats on top of another magnet. So in this wooden box, there's some magnet hidden. So this magnet spinning in the magnetic field of these magnets here, it's very similar, like our atoms are trapped in the center of our chamber. They float in free space, just held because they have a little magnetic moment. It's the best thermist you can imagine. There's no walls that have to hold these atoms. They're completely free. There is nothing physical that talks to them. And that's why we can reach these absolutely low temperatures. But we actually want to cool them down to even much lower temperatures. So how do we do that? Well, we could simply wait. Like a coffee in a coffee cup. And we wait, well, the hot coffee particles, they will leave, and the cold ones will remain, and get colder. That's how we cool our coffee. In our case, we can actually force this process by essentially blowing on our coffee.
Once the atoms are trapped in the magnetic field, the gas has an average temperature of about a millikelvin, but the speed of individual atoms varies. When Zweerlin applies a certain radio frequency to the trapped atoms, it essentially acts as a razor, shaving off the hotter atoms and leaving the cooler ones. The remaining atoms will then reach a lower average temperature, and Zweerlin can repeat the process, reaching lower and lower temperatures. This process is called evaporative cooling. Once the lithium atoms have reached the right temperature, they can test if they are superfluid by stirring the atoms. We are all familiar with what happens to a liquid, coffee for example, when it is stirred. All of the liquid will rotate, the velocity increasing smoothly from the center to the outside.
So if you rotate a cup of coffee, nothing special happens. It just rotates, as we say, a rigid body, in a boring way, so to speak. If you rotate a superfluid, it can only rotate by developing quantized mini tornadoes that pierce through the superfluid, and many of them.
So if Zweerlin sees these quantized tornadoes, or vortices, in the systems he's working with, then he will have direct confirmation that he has a superfluid. Zweerlin stirs his atoms not with a spoon, but with lasers.
The laser beam goes through two crystals. These two blocks here contain crystals that can deflect the laser beam, and we can now diffract the light more or less, up or down or left or right. Essentially, we can paint any kind of pattern onto our atoms. And of course, if you want to rotate your cloud, you should use a rotational pattern. Just go around in the circle. So it's really, literally like taking a spoon and rotating it in your coffee mug.
When Zweerlin and his team took a picture of the stirred lithium atoms, this is what they saw.
After a while, after the gas has equilibrated in this rotating frame, it will start to develop these vortices. They will creep in one after the other from the outside and start to form this beautiful vortex lattice.
This was the first direct evidence that strongly interacting fermions are, in fact, superfluids. It's just one example of how the extreme conditions made possible by laser cooling and trapping have enabled Zweerlin and other physicists to create model systems in which they can manipulate atoms in ways never before possible.
You can tickle the atoms, play with them, and add yet another laser beam and see what happens. You can see how nature reacts to this unusual situation in which you place her. So it's this immense control that we have. The fact that we can make quantitative experiments that really give a number, a hard number that we give to theorists to say, okay, please, you should get that. This is the outcome. Does your theory get that? This is one motivation, this comparison to theory. The other motivation is find new exotic states of matter that no one has actually started to think about. No one